Okay, welcome to Wednesday, November 11, and we're finishing up our discussion this week of trigonometric equations. These are problems where I have to find the value of a trigonometric function and then find the value of the angle that satisfies the equation. So I'm solving for a value and then solving for an angle. And we gave you the illustration last time that you need to make sure that you're using the interval they want you to use, that you're using the format they want you to use, and that you're reporting your angles either exactly or approximately as they intend. So that last example we came up with last time where we actually produced an answer that was extraneous, an answer that was false. So we got to look into that again, try to produce another one like that. But first, I'm going to give you some other examples. So let's get out our handy formula sheet, because we're using all of these formulas for sum, difference, double identity, and half angle identity. And we're not going to be using product to sum and sum to product as much in this context. Those are things that are used more often in the graphing context. Okay, let's go back and just warm up on one. And I'm looking at 6.2, number 2. Square root of 2 times the cosecant of theta equals 2. And they express this problem in theta. So he wants all degree solutions from 0 to 360. From 0 degrees to 360 degrees. And I bring this problem up here because it's a short problem, just to get us back into the swing of doing these. So what's the procedure? Let's find out what cosecant is, then let's find out what theta is. So if I divide both sides by the square root of 2, I can simplify this right-hand side. You could literally think of 2 as root 2 times root 2. So when you see 2 divided by root 2, you have to acknowledge that that's equal to root 2. And now I need to draw an angle whose cosecant is root 2. Now let's see, what is a cosecant? Cosecant is the reciprocal of sine. So if the cosecant is root 2, then the sine of that angle is 1 over root 2. Now I have to draw that angle. And that's a famous angle with a y over r value of 1 to root 2. That's a 45, 45, 90 triangle. So this could look like this. 45 degrees with a terminal point of 1 and 1, because I go 1 over and 1 up. And the radius is root 2. That angle, which is 45 degrees, has a cosine of 1 over root, as a sine of 1 over root 2. So it has a cosecant of root 2. But there's another angle whose sine is 1 over root 2. And that's in the second quadrant. So I need to find all the angles between 0 and 360 that satisfy that. Then I draw this reference triangle like this. The x-coordinate is -1, the y-coordinate is 1. The sides of the reference triangle are 1 and 1 still, 45, 45, 90. Radius is root 2. And this angle is 45 degrees short of 180 or 45 degrees past 90. This is 135 degrees. Okay. These are the only angles that have a cosecant of root 2 between 0 degrees and 360 degrees. Okay, so you want to state the answer finally. You got 45 degrees and 135 degrees. They wanted this answer in degrees. Okay, I also want to illustrate this answer for a particular reason, and that is, unless I know these famous triangles, I don't have any method of doing this problem. So from the beginning of the course, we've worked with the famous triangles, 30, 60, 90, 45, 45, 90, and even 15, 75, 90, although the book uses that much less. So you need to know, it's actually a requirement that you draw these angles in a standard position as I've done, and that you can label the sides and label the points on the terminal side. And I think there was some confusion in some places among the most recent homework when I asked you to draw an angle. I had some people that were drawing, wavy lines like this. This might be the graph of a sine or cosine function, but it's not an angle in standard position. So if you need to review how to do that, you go back into chapter 1 in early sections like 1, 2, 1, 3, 1, 4. Oh, let me give you a direction here. When you were drawing angles in standard position and labeling their sides, and that's problems like section 1.3, example 1, example 2, example 3, example 4. So I'll write that down. Be sure that you can draw and label any angle described to you in standard position. And I'll just send you back to section 1.3 if you want to need a reminder. This is a famous angle, so I right away named it as 45 degrees. It doesn't mean that every angle I have to draw might be one of the famous ones. But in that case, if I have to estimate, I do have the calculator. Okay, let's try another problem. So involving sines, cosines, involving other functions as well. Let's look at 14. 6.2, number 14. And I'm going to build our way back to that problem we reached at the end last time where we created an extraneous answer, an answer that didn't work. So 14 says cosine of 2x minus the cosine of x minus 2 equals 0. And they give you the problem in terms of x. So they want the answer in radians between 0 and 2 pi. Okay, the first thing I have to do in this problem is resolve the fact that I've got two different angles. Here's a 2x, here's an x. You know, which angle do you want me to find, so to speak? But so I have to kind of organize the problem so it's only talking about one angle. So this is where I have identities to help me. I know an identity for the cosine of 2x. In fact, I know 3 identities for the cosine 2x, which in some ways makes it a little bit harder because I'm going to have to choose which one I want to use. But I'll tell you how to make the choice here. So these are the 3 identities for cosine 2x. And as I recall these right here, 2 of them I would just immediately reject. Okay, let someone else in the room here. There we go. 2 of these formulas are non-starters because they're not going to help me make this problem simpler. This first expression, cosine squared x minus sine squared x, it's true, and I can write it here. But then I'll introduce a third piece. I'll have a cosine squared, and a sine squared. And so I've tried to make this look simpler, not more complicated. The last piece involving the sine squared. Again, I don't want to create a problem that has sine squared and cosine in here if I can avoid it. I'd like to focus the problem just on the cosine of x. This is the identity we want to use, because then I'll have the whole problem written only in terms of cosine of x. So let's replace that with 2 times the cosine squared of x minus 1. And I still have this minus cos x. And I still have this minus 2. Now you can complain that you introduced a square there. That makes it more work. Yeah, but we've already done a couple with the quadratic formula. So this doesn't seem impossible to me. Let's gather together any like terms I have right here, like minus 1, minus 2 is minus 3. So let's rewrite this as 2 times the cosine squared x minus the cosine x minus 3 equals 0. Now it's possible I could factor this besides using the quadratic formula. So I want to see if I can factor this. I want to see if I think about this. You know, think about this as 2 times something squared minus something minus 3 equals 0. Can that expression be factored? Factoring is always faster than the quadratic formula. So let's see if we could factor that. Maybe 2u times u, give me the 2u squared. And 3 can only be made 1 times 3. But I think I need to put the 3 there and the 1 there. I want a negative 3, so one of these has got to be negative. And I want negative u in the middle. So I want negative 3u and plus 2u. Is that a legitimate factoring? Got the 2u squared? Yep. Minus 3u plus 2u is minus u. Yep. Minus 3 times plus 1 is minus 3. Okay, that's positive. That means I can factor this, and I don't necessarily have to fill in the quadratic formula. So let's factor this and think of this, instead of u, Think of that cosine of x as what I just called u. So I get 2 times cosine of x cosine of x plus 1 minus 3. Okay, good. Here I have 2 things multiplied together, give me 0. By the zero product principle from your algebra class, one of these has got to be 0. In fact, the only way to multiply 2 things and get 0 is if one of them is 0. So this breaks down immediately into 2 cosine x minus 3 is 0, or cosine of x plus 1 is 0. I get another lucky break right here. If I add 3 to both sides, I get 2 times the cosine of x is 3. And the cosine of x then is 3 over 2, 1.5. So this is related to the problem we did at the end last time. Do you realize there is no angle that has a cosine of 1.5? Cosine is always between -1 and 1. So in this branch, I don't have any angles that make this sentence true. Cosine of x equals 3/2 is impossible. Okay, so now let's finish this side. Cosine of x is equal to -1. And that's a famous angle. Remember, cosine is x over r. But if the cosine is at its very bottom, -1, that's not a triangle so much as it's what? One of the quadrantal angles. Which angle has a cosine of -1? It's 180 degrees. Now they want us to talk about radians, right? So let's call it pi radians. There's no triangle for me to draw there, but if you want to label this point, you can label that distance 1. You can label that point -1 and 0 because the x coordinate's -1 and the y coordinate is 0. It doesn't go above or below the x-axis. And in between 0 and 2 pi, in between 0 and 360 degrees, this is the only angle whose cosine is -1. So x equals pi is the only response I get to this problem. Now, like last time, I want to always emphasize that we can check these either on calculator or on Desmos. So I'm going to open up Desmos, and I'll share the window with you just to verify that we haven't missed anything. So let me open up Desmos window with you. And the problem was y equals cosine of 2x minus cosine of x minus 2 equals 0. They want to know when this curve is equal to 0. Now remember, they wanted to know on the interval 0 to 2 pi. So let me add that so I don't see all this repeating. On the interval 0 less than or equal to x less than or equal to 2 pi. Just type pi as lowercase p, lowercase I. Okay, here's my graph. Feeling better. Let's get the scale right. I'm in radians, good. X-axis, let's just go from 0 to 2 pi. And I don't mind what step I use, but let's say pi over 2 if you like. There's a picture of that graph from 0 to 2 pi. And there's only one place where that graph is equal to 0. And that's right there at pi when x is equal to pi, then y is equal to 0. Okay. So there was an extraneous solution right here, if you want to think about it. Whenever you come up with an answer that doesn't work, you could call that an extraneous solution. I'm not ready to commit to calling this an extraneous solution because actually I didn't even get a solution out of this. So it's hard for me to call this a solution that didn't work. Rather, this branch of the problem just didn't produce anything. Okay, let's try 2 more so I can get my way up to that one problem I was looking at. I want to look at 21 here. 6.2, number 21. So 2 more problems in this section, then we'll work on the next. Here's 2 times the sine of x plus the cotangent of x minus the cosecant of x equals 0. Let's try this problem. So they want all solutions in radians between 0 and 2 pi. Okay, so 3 different trig functions. Again, I had to resolve this somehow by writing this in terms of one function. So first step, I could remember cotangent is cosine over sine, and cosecant is 1 over sine. So let's write this as 2 sine x plus cosine x over sine x minus 1 over sine x. Okay, you say you made it worse by adding fractions. Let me go back to my paper. I included fractions in here, so at first glance it makes it look worse, but actually it's a little bit better because now I just have sine x and cosine x. Maybe I could do something to get that down to one function. Before I do that, I'm going to look at this first expression here. Common denominator sine x already here. Let's make this common denominator sine x. So if I multiply top and bottom by sine x, I get 2 sine squared x over sine x plus cosine x over sine x minus 1 over sine x. And now I spot an identity. So let's make one fraction, 2 sine squared x plus cosine x minus 1 divided by sine x. And remember the principle from algebra. A fraction is 0 only if the numerator is 0. So now I can just focus on the numerator. But I see that identity I just wanted to use earlier. Cosine of 2x was what? 1 minus 2 sine squared x. So I'd like to write this numerator just in terms of one function. I'm either going to replace the sine squared or I'm going to replace the cosine. So I'm going to go through some identities that have sine squared in them and decide which ones would be the most useful one. What other identity has a sine squared in it? Pythagorean identity. Cosine squared x plus sine squared x is equal to 1. With that, I could replace sine squared x with 1 minus cosine squared x. Then I would have a numerator that only involves cosine x. I think I'm going to choose that one. I could use this 2 sine squared x. That's to be true, but I don't want to create another cosine 2x in here. I go back to the last problem where I have to eliminate it. So let's replace sine squared x with 1 minus cosine squared x. So this fraction equals 0 only if its numerator is 0. And the numerator is 2 times 1 minus cosine squared x plus cosine x minus 1. Okay, let's multiply that out. And I get 2 minus 2 cos squared x plus cosine x minus 1 equals 0. We're going to look at a quadratic expression. I'd like to lead with a positive number, but first let's combine the 2 and the 1 negative. Now I have negative 2 cosine squared x plus 1 cosine x. 2 minus 1 is plus 1 equals 0. And now let's multiply everybody by minus 1 just so I can lead with a positive number here. 2 times the cosine of squared x minus cosine x minus 1 equals 0. Now what am I looking at with this quadratic equation here? Oh, I wonder if this factored. So think about u in place of the cosine x. Could you factor something if it said 2u squared minus u minus 1 equals 0? And if it doesn't factor, I'll use the quadratic formula, but let's see if this factors. The numbers are so small that it's worth trying. 2u times u. The only way to make 1 is 1 times 1. I want minus u in the middle, so how about minus 2u and plus 1? Is that a legitimate factoring? 2u squared, yes. Plus u minus 2u is minus u, yes. Plus 1 times minus 1 is minus 1, yes. So this is a legitimate factoring, and that means I can break this down. So everything that you've learned to factor previously, you have to remember how to factor now. So I'll write that as 2 cosine x plus 1 equals 0, or cosine x minus 1 equals 0. If I subtract 1 and divide by 2, this says cosine of x is minus 1/2, and I can draw that angle. I can draw two angles that have a cosine of minus 1/2. One, hypotenuse 2. This would be a 30, 60, 90 triangle through the point -1 and √3, or a 30, 60, 90 triangle with the same adjacent side, the same long side, but the y value this time would be -3, negative √3. So here are two angles that have a cosine of negative 1/2. And they are 2 pi over 3, 2/3 of the way to pi, and 3 pi over 3, 4 pi over 3. This angle right here is 4 pi over 3. It's pi over 3 past pi. Okay, so I've got those two angles. There's no other angles between 0 and 2 pi that have that cosine. On this branch, cosine of x is 1, but there's only one angle that has a cosine of 1, and that is the very first angle. 0 radians, or 0 degrees. And it's not really a triangle here. This is a quadrantal angle. So this x is 0. So now I've got my three answers. X equals 0, x equals 2 pi over 3, and x equals 4 pi over 3. I want to verify this in the graph. So let's go back to the beginning, graph this equation, and see if these are legitimate. Now, remember, I always got to check to see if something went wrong with my work. Do you remember we said this yesterday or Monday too? I can only make this fraction 0 if the numerator is 0. But I also got to forbid you from letting the sign of x be 0. Because if the sign of x is 0, I don't even have a fraction. And now as I look at my answers, here, the sign of 2 pi over 3 is root 3 over 2, no problem. The sign of 4 pi over 3 is negative root 3 over 2. But the sign of 0 is 0. I can't use this as an answer. And why can't I use it as the answer? Because the sign of 0 is 0. And so cotangent of 0 is not defined, and cosecant of 0 is not defined. So I thought I had three answers, right? I've got to throw that answer out. The cotangent of 0 and the cosecant of 0 are not defined. So that's not a legitimate answer. So now I just have two answers. So there's a good illustration of creating an extraneous answer, creating an answer which actually doesn't work in the original problem. You always have to check your work against the original problem. But let's graph this. If I hadn't noticed that, I would have discovered it by graphing this. Let's go back and graph it. Okay, so I'll keep the 0 to 2 pi right there, but I'll type in 2 sine x plus cotangent x minus cosecant x. That's kind of a pretty graph. And I'm kind of curious about how this looks. Here's from 0 to 2 pi. When does this equal 0? It certainly equals 0 here at 2 pi over 3 and 0. And it certainly equals 0 here at 4 pi over 3 and 0. Now, you get this feeling from the graph that you could use x equals 0 or x equals 2 pi. But I know that the sign is forbidden at those values because the sign would be 0. Let's expand this a little bit and see. So far, Desmos has always told me the truth in the graph. Let's take off this restriction. That's kind of interesting, isn't it? Desmos tries to report a value to me at 2 pi. Now, I won't blame it yet. Let's try to touch 2 pi. So if I actually touch 2 pi, that's interesting. It's not responding with an error at 2 pi. Let me back out of there. Let me ask Desmos what would happen if I put 2 pi in there, or if I put 0 in there. That's interesting. When I type in 0 for x, what does Desmos do? Desmos admits that that's undefined. Okay, so right there, it admits that that's undefined, but it didn't seem to admit that it was undefined at 2 pi. Let me type in the 2 pi. Okay, so you got to be careful even if you're using the calculator to back you up. Okay, it admits when I type it in that it's undefined. But look at that graph. It does not tell me that that's undefined at 2 pi. Okay, so be careful with the answers you produce, even when you check them here on the graph. You always have to use a common sense. Other than that, I think it's a beautiful graph. It's got a nice little repeating pattern to it. Okay. So there's an example of an extraneous solution. Always check to make sure all of your solutions work. Okay, one more here in this section. And this was like the one we ended with last time. And then we'll go on to section 6.3. This is number 29. And I want all solutions. I go back to my paper. 0 less than or equal to x, less than or equal to 2 pi. Sine x over 2 minus cosine of x equals 0. Okay. I can't have this half angle and full angle. I have to resolve this so that I'm only talking about one angle. So let's get out our sine of half angle formula. Plus or minus cosine 1 plus cosine a over 2. Now the trouble we had last time was the plus or minus and the root here. So I'm using this identity. Sine of x over 2 is equal to plus or minus the square root of 1 minus cos x over 2. And I can insert that into here, but then I have to deal with the plus minus and the square root. So I wanted to show you this problem, or one like it again. Last time we did 31. Now, if I put the cosine x on the other side, say plus minus the square root of 1 minus cosine x over 2 equals cosine x. I'm allowed to square both sides of this equation. And at first, that's attractive because when I square the left side, then I say, okay, I don't have to worry about the plus minus anymore. It just becomes positive. I don't have to worry about the square root anymore. It's just 1 minus cosine of x divided by 2. But there's this warning that we gave you last time. Even though it's legal to square both sides of an equation, if you have two things that are equal and you square them, then they remain equal. You haven't caused any damage. But sometimes you could square two things that aren't equal. And after you square them, they look equal. So by squaring both sides, you could take something that's false and turn it into something that's true. So when you square both sides of an equation, you may create false answers. That's what we're going to have to look out for. Okay, let's finish this off right here. 1 minus cosine x is 2 cosine squared x. Let's bring these two pieces to the other side. 2 cosine squared x plus cosine x minus 1 equals 0. We've done a couple factorings today. I think this one factors into 2 cosine x, 1 times 1 is 1. Give me a plus 2 and a minus 1. Always check your factorings. 2 cos squared, yes. Minus cos x plus 2 cos x is plus cos x, yes. Minus 1 times plus 1 is minus 1, yes. So this is a legitimate factoring. And I get 2 possibilities. 2 cosine x minus 1 is 0. Or cosine x plus 1 is 0. If I add 1 to both sides, divide by 2, cosine x is 1/2. And I know 2 angles that do that. Angle of 30, 60, 90 with cosine of 1/2. That's 60 degrees. Or an angle 30, 60, 90 where I have cosine of 1/2 in the 4th quadrant. The name of this point is 1 and minus root 3. The name of this point is 1 and root 3. We're talking about radians. This is 60 degrees, or pi over 3. This is 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3. And I still have to check both of those. But let's draw this angle before we check. This says the cosine of x is equal to minus 1. That's a special quadrantal angle. That's exactly at pi, or 180 degrees. So here are my 3 possibilities. X equals pi over 3, x equals pi, 5 pi over 3, pi, whichever. It doesn't matter what order I write them, or x equals pi. I'm a little bit nervous about these, so I'm going to test them out. For example, at pi, the sine of pi over 2 is what? 1. The cosine of pi is minus 1. So what's the sine of pi over 2 minus the cosine of pi? Sine of pi over 2, 90 degrees, is 1. Cosine of pi is minus 1. So 1 plus minus 1, I'm sorry, 1 minus minus 1 is 2, and not 0. So I'm nervous about this one. I don't think this one works. Let's try these two. Let's try sine of pi over 3. So if I put pi over 3 into here, I get sine of pi over 6. Minus cosine of pi over 3. What's the sine of pi over 6? That's 1/2. What's the cosine of pi over 3? I'm looking at pi over 3 right here. Cosine of pi over 3 is 1/2. So 1/2 minus 1/2 is 0. This one works. Let's try 5 pi over 3. half of 5 pi over 3 would be 5 pi over 6. What's the sign of 5 pi over 6? Minus the cosine of 5 pi over 3. The sine of 5 pi over 6 is 1/2. And the cosine of 5 pi over 3, I'm looking at 5 pi over 3 right here. The cosine of 5 pi over 3 is 1/2. So 1/2 minus 1/2 is 0. This one appears to work. So you can't predict which one was going to fail. I was ready to say, oh, one of these fails and these two are correct. Now let's go and get some visual confirmation of this. But it looks like my only two answers are pi over 3 and 5 pi over 3. Back to the calculator. Sine of x over 2. Get my parentheses correct. Minus cosine of x. I got this greatly expanded, right? So let's blow this up. Let's just zoom in on x between something like -3 to 3. That's where things seem to be happening, or y between -3 and 3. Okay, good. Now let's look just between 0 and 2 pi. Already these answers look good. Pi over 3, 5 pi over 3, possibly. But I want to get rid of this other stuff. Let's just look between 0 and 2 pi. Okay, good. Now I could expand this graph if I wanted to. Let's just run it visually from 0 to 2 pi. And let's set the step at pi over 3 and see what Desmos will draw for me. There's two crossing places. At pi over 3, 0. And at 5 pi over 3, 0. Those are the two solutions. Pi turned out to be something else entirely. In fact, when I calculated and checked pi, didn't I get 2 when I plugged in pi? And Desmos is admitting, yes, if you plug in pi, you get 2. Okay, very good. So you can, well, I don't want to say you can always trust the calculator, because in the last problem, I got some odd response, something that seemed to be defined where it wasn't. But here, at least, you're visually checking that you have the two answers. Okay, let's go into some problems in section 4.3 that require a little more work. And these are problems that involve either multiple angles or other identities. Let me give you an example. And I need another pad of paper. Excuse me, grab another pad of paper here. Let me show you how this starts. So a lot of problems in this section say sine 2x, sine 3x, cosecant, etc. Let's look at problem number 5. Just practicing solving trigonometric equations. Cosine of 3 theta is -1. And they want all the solutions between 0 and 60. Okay, what am I supposed to do here? Because I don't have any identities with cosine of 3 theta in them. But I do know when cosine is -1. So that's what I should focus on. Let's draw a picture of when cosine is -1. And that will be the angle that I seek. Well, it will be 3 times the angle that I seek. So if I draw a picture when cosine is -1, what am I drawing a picture of? I'm drawing a picture of 3 theta. But if I can tell you what 3 theta is, maybe I could determine what theta is inside this boundary. So let's draw a picture where cosine is -1. Again, that's a quadrantal angle. So cosine is -1 means I'm talking about this special point over here. I'm using degrees right now. So we're at 180 degrees. And so maybe this is 3 theta, right? So you're kind of happy. So you write on your paper, 3 theta is 180 degrees. But when you get it back, someone marked it wrong. Why would they mark that wrong? Because they didn't ask you what 3 theta was. They asked you what theta was. And let's think about this very carefully. There's 2 things I got to do to finish this problem. It's not wrong to say 3 theta is 180. But they asked me what theta was, so I have to finish this. I have to say, oh, you mean theta is 60 degrees. But that's not the only answer to this problem necessarily. 3 theta could have been 180 degrees, but 3 theta could have also been 540 degrees. I could have gone around and then landed on 180. So is that a legitimate answer? What happens if 3 theta is 540? Well, I divide both sides by 3. So I get theta is 180. So I get 2 answers right now. I got 60 degrees. I got 180 degrees. I wonder if I should try for another one. What's 540 degrees and another trip around? What else is coterminal with 180? 180, 540. Let's go another circle around. That would be what? 540 plus 360? That's 900 degrees. Could 3 theta be 900 degrees? Well, if it is, I divide both sides by 3. Theta equals 300 degrees. And that's a legitimate answer because 300 degrees would be over here. What you get is 3, kind of beautifully equally spaced answers. 60 degrees, 180 degrees, and 300 degrees. Each one of those makes 3 theta have a cosine of -1. So I'm not using an identity here, but I'm saying I have to find all the answers for theta between 0 and 360. You say, well, maybe there's another one. Maybe I should look for another one. Okay, add 360 again. Give me a 1260. Could 3 theta be equal to 1260 degrees? Well, that would give me theta equals 420 degrees. This would work. It would be back here at 60 plus 360. But that's beyond what they asked for. So these are the only three answers that I have right here. Now you still feel nervous about guessing answers like that. So here's how you could manufacture that answer without guessing it. What you could have said was 3 theta is got to be 180 degrees, but it could have been 180 degrees plus any multiple of 360, right? That's the 180, 540, 900, 1260. And if I add this k times 360, I'll account for all these angles. Watch what happens when I divide by 3. Well, then theta, 180 divided by 3 is 60 degrees. And 360 divided by 3 is 120 degrees. So here are all three of those angles. Now for every k, I have to say what? For k equals 0, which gives me the 60. K equals 1, which gives me the 180. And k equals 2, which gives me 240 plus 60 is 300. I don't use any more k's. If k is 3, I get 60 plus 360, which was too big. That's the 420. If k is minus 1, I get 60 minus 120, which is minus 60, and that also wasn't in there. So remember how we could write all the answers to a problem here? In this case, that helps us discover all the answers to this problem between 0 and 360. Okay, this is the technique they're going to use on this problem all through this section. Now, I do want to emphasize that I can still graph this and see those three answers, 60, 180, 300. So let's graph cosine of 3 theta. Back to screen. Cosine 3 theta. Sometimes Desmos objects when you use another letter. Let's run this 0 to 360. But we did try to write in degrees last time in Desmos, and it was okay as long as I hit this degrees button. And describe my degrees from 0 to 360. And let's describe my step sizes every 60 degrees. Okay, let's see what we got here. Well, what should I have for cosine 3 theta? I should have 3 cosine waves in one full period. One full period is 360 degrees. There's 1 cosine wave, 2 cosine waves, 3 cosine waves. Good. Now, what about my answers right here? When is this equal to minus 1? Not when it crosses. I was interested in when this equals minus 1. That's these 3 parts right here, 60 degrees, 180 degrees, and 300 degrees. So that confirms the 3 answers that I have. Okay, very good. Let's try it again. I'll try something like 11, like 17, and then let's get into these later ones right here. 25, 27, 19 to 21. Let's try 17, because that kind of looks obnoxious. And I think it's similar to what we just did, but it kind of looks obnoxious. 6.3 over 17. The sine of 10 theta, so he decides to go crazy right there, is root 3 over 2. And they want all degree solutions. Now this is a different instruction that we received before. All degree solutions. They didn't say all solutions between 0 and 360. They just want all the answers, period. They want every angle such that 10 times the angle gives you root 3 over 2. Sorry, let me switch back to my paper. Can you find every angle that when you multiply by 10 and take the sign, you get root 3 over 2? Well, again, you have to base this on what? Your knowledge of sine. When is the sine equal to root 3 over 2? It's 30, 60, 90 triangle. So we're talking about this angle right here. Root 3, 2, and 1. That point right there is 1 and root 3. And we're talking about its mirror image over here. Root 3, 2, and 1. But this point is minus 1 and plus root 3. Now they did say degree solution, so I'm allowed to think in degrees. This is 60 degrees. And this is 120 degrees. But this is not theta. This is 10 theta. These two angles are 10 theta. The sine of 60 degrees is 320. So that means 10 theta is 60 degrees, or 10 theta is 120 degrees. Sorry, 120 degrees. But remember, to capture all the possibilities, I'm going to add k times 360, k times 360. So let's find all the possible answers here. Divide everybody by 10. So I get one set of answers that says 6 degrees plus any multiple of 36 degrees. And I have another answer here that says 12 degrees plus any multiple of 36 degrees. Now, the 6 degrees and 12 degrees is hard to visualize, and the 36 is hard to visualize. So let me see if I could draw that for you before we test it. Now, I don't have to restrict my k because they wanted all solutions. So every time I pick a k, I get a legitimate answer. But what would this look like visually? Six degrees is very small, and I don't even know if I can draw it, honestly, right? Why don't I call that 6 degrees? I don't think that's exactly 6 degrees, but let's make it a small angle. Where it's going to be 12 degrees. Well, I don't think I can draw that any better, but I better make it at least twice as big as my 6 degrees, right? So let's try that for being 12 degrees. So what does the k times 36 do then? That means I add 36 and get an answer. That's 42 degrees. That means I add 36 again and get an answer. What's 42 plus 36? 78 degrees. How many things will I add in 360 degrees? I would have to pump this k up to 10 until I get back to here. So what I need to draw is like 10 equally spaced angles based on 6 degrees. And I don't even think I can draw this perfectly, but let's take the circle and cut it into 10 pieces starting right there. Well, that might be 2 pieces. And I got to cut this into 5 pieces, right? So 72, 6. What's 72 plus 6? 78. I really don't think I'm qualified to draw this. You know, this is the kind of thing where I think I'm going to let a computer draw this. But that's not too bad. That's 5 spaces. And here comes another 5 spaces. Maybe I shouldn't be too proud of this. Here's 42 degrees. Add 36. 78 degrees. Add 36. 114 degrees. Add 36. 150 degrees. Add 36. 186 degrees. Add 36. 222 degrees. Am I adding correctly? Check me to make sure I'm adding correctly. Add 36. 258 degrees. Add 36. 294 degrees. Add 36. 330 degrees. Add 36. Okay, that's 366 degrees. Now I start repeating myself. Okay, if I succeeded with the purple ones, now I'm just going to draw red ones that are right next to the purple ones. 6 more degrees would be 84 degrees, 48 degrees. Now, the reason I'm drawing all these is because I want to show you when I see the graph that I should see all these answers. But there's so many answers here. How many answers am I drawing just between 0 and 2 pi? 10 purple ones, 10 red ones. I've got 20 answers right here. And I could name all the red ones too, but I think I'm going to let that be. Do you see that's why people invented this writing? So you don't have to write down 20 different answers. Well, let's try this out. Let's take this and graph this and see if I can have 20 different answers between 0 and 360. Now, this accounts for all the answers. Here, I haven't even drawn them all because I could keep repeating and repeating. But this accounts for all the answers, but I want to see at least 20 answers. Well, I want to see exactly 20 answers between 0 and 360 degrees. Okay, so sine 10 theta, let's try it out. Coming over here, sine 10 theta. That's why there's so many answers, because that's 10 sine waves in 360 degrees. Count the peaks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sine waves between 0 and 360. And now what do I want for this? I want it to be equal to root 3 over 2. Square root of 3 divided by 2. And here are my 20 answers. I don't even think I could touch them all because it's too crowded there. But there's 12 degrees, 42 degrees, 48 degrees. See, this graph is going to be so crowded now. I can't even mark them all, but you see them. I can't even touch that 6 degrees there. That's kind of disappointing. There it is. Okay, touch the 6, touch the 12, touch that, touch that. Okay, maybe I can touch them all. No, it's too crowded. But you see answers 6, 12, 42, 48, 78, 84. Those are the answers I marked on my paper. Okay. So this is tell you the value of this expression k times 360. When you say that any angle plus any multiple of 360 works, then when you have multiple angles here, that helps you describe the multiple angles. That's 20 angles, even just between 0 and 360. Okay, so that's a fancier problem. Let me try one with another identity in it. 19 through 22 is important. And if possible, I think you should also do examples 29 through 33. So let's just pull a couple out here because probably have more problems to do than we have time to do them. Let's try number 21. So you can try all these, but now he's getting into a lot of goofy extra problems here. Different kinds of identities. When he gives you this problem in 21, what identity is he referring to? Okay, cosine 2x cosine x minus sine 2x sine x equals negative root 3 over 2, and he wants all the answers between 0 and 2 pi in radians, exact values only. Well, this reminds me of this identity. So you may not have to memorize every identity, but you have to recognize them when you see them. I recognize what? The cosine of a sum or difference. Now, which one is it? With the cosine formula, it goes cos, cos minus sine, sine when you add the angles. So he's adding the angle 2x and the angle x. So this whole expression right here turns out to be the cosine of 3x. And now the problem is more recognizable. When is the cosine of 3x equal to minus root 3 over 2? Again, it's time to draw the angle. No drawing the angle, no answer. So I need to know the angle whose cosine is minus root 3 over 2. That's a 30, 60, 90 triangle, but cosine negative means back here. And cosine is the x portion, so the longer portion, the root 3 is in the x direction. The 1 is in the y direction, and the hypotenuse is 2. The name of this point is minus root 3 minus 1. The name of this point is minus 3 plus 1. So these two angles right here, this is the 30-degree angle right there. So the angles that we're talking about are 150 and 30 degrees past 180, which is 210. Now be careful, that's not x, that's 3x. 3x is 150, or 3x is 210. See, I got to go back to radians again. I'm naturally thinking in degrees, right? Well, 150 degrees is 5 pi over 6 radians, and 210 is 7 pi over 6 radians. But that's the 3x, and I got to find all the angles between 0 and 2 pi, so I got to modify that again. 3x is equal to 5 pi over 6 plus k times 2 pi, or 3x is equal to 7 pi over 6 plus k times 2 pi. Now I divide everybody by 3. And the first equation will say 5 pi over 18 plus k times 2 pi over 3. 2 pi over 3 is 120 degrees, but I have to write in radians. He wanted me to write in radians. And the other angle is 7 pi over 18 plus k times 2 pi over 3. This is going to be similar picture to the last one, just not so many angles. If you think of 5 pi over 18, now what would it mean to divide pi into 18 pieces? You know, that's really, really small. And I'm going to think about 150 in degrees just so I can wrap my head around it. If I divide 150 by 3, I get 50. So that must be 5 pi over 18. But then plus 120 degrees and 120 degrees again. So what I have is like 3 equally spaced angles. This would be 5 pi over 18 plus 2 pi over 3. I change that to 18, it's 12, so this would be 17 pi over 18. And then plus 4 pi over 3, give me a 6, give me a 24. That's 12 pi over 18, this is 29 pi over 18. I don't think I drew that is nicely split into 120 degrees. I think this one should be farther down. That's not beautiful. Here's a 7 pi over 18, maybe slightly larger. 7 pi over 18 is 70 degrees because 210 divided by 3 is 70. So there's 7 pi over 18. And then add 12 pi over 18 is 19 pi over 18. Then add 12 pi to that is 31 pi over 18. So this k times 360, k times 2 pi divided by 3, do you see what it does for you? It tells me I had 2 sets of solutions and they were equally spaced at 120 degrees from their base solution. Now, I could write down all 6 solutions as I just did. And they wanted only the answers from 0 to 2 pi. So I guess I should write down either the k is 0, 1, or 2 in this formula, Or I should write down exactly what these 6 solutions are. I've changed up my colors. So I'll just keep them all purple. And before I end, I want to show you on the image that I can see that these are correct. So there's the 6 answers. Let's go and graph it. And I'll come back to the page if I need the formula, but how'd the formula be going? Cosine of 2x times cosine of x, not cow of x, minus sine of 2x times sine of x. Let me pull this, I can pull this window out over here so I can see things better. And then I'll make it smaller when I want to see the graph. So this was the original function. And I wanted to know when that was minus 3 pi over 2. Got it. Okay. And I want to talk about radians, right? So I'm going to say x less than or equal to 2 pi. Okay. Now I'm going to make this graph smaller and go back to radians in my graph. And that means I have to significantly change the scale, 2 pi. Now it's starting to look normal. I don't think I can tell Desmos to graph every pi over 18. I mean, I can try, but Desmos doesn't have to obey. So let's see what I got. I do have 3 cosine waves, cosine 3x. What are these points right here? Pi over 6. Oh, no, I'm not interested in when it's equal to 0. Okay, good. Don't make that mistake. I'm not interested in that point. I'm interested in when it's equal to minus there. 5 pi over 18, 7 pi over 18, 17 pi over 18, 19 pi over 18. And in some sense, Desmos is too kind to you. It just gives you the answer outright. Now, for that reason, if you just brought me those 6 answers, I would, frankly, I'd give you no credit at all. You have to show me how to make the 6 answers as we did on the paper. But if you want to think about it as like glass half full, at least Desmos told you that the 6 answers you found were correct. Okay, so you got backup. You just have to make sure that you can do this calculation. Okay, there are other things we could do right there, but we've reached our time and we're not going to go past it. So I'm going to let you start working on this. And I'm going to get this recording wrapped up and posted. I'll also post these notes that we've drawn here online. Don't forget that you always have the notes. As you're doing your next week's homework problem, make sure that you look at the answer that I've posted to the one you handed in last night, because the one you're going to hand in next week is similar to the one you just did as far as having to draw things. And I'm really emphasizing right now you drawing the angles. So make sure you look at the way we drew the angles and described them in the homework problem that you just handed in last night. Okay, I will see you guys next week. You have a good weekend. Stop that sharing and end this recording.